Well, hello and welcome back to the Dragonfly Daily. I am Mike Marsh, the product manager at ORS, and you can follow me at Dragonfly Wizard on Twitter. Be sure to check out the YouTube page, orss.ca/YTP2, where you can find the channel with all of the Dragonfly Daily videos. And while you're there, go ahead and subscribe to the channel so you can get other content on Dragonfly from the team at ORS. Today's topic is Lesson 36 CT Reconstruction. If you are watching on YouTube right now, hit that subscribe button and go ahead and give us a like so that we can continue to produce high quality content and the bosses will keep approving me to work on content like this. Lesson 36 CT Reconstruction. This will be done using Dragonfly 2020.1, the release candidate that we made available earlier this week. CT Reconstruction. This will not be a lesson in CT Reconstruction math or CT imaging physics. There are plenty of lectures like that available on YouTube, and we don't have time to do that in a 15 to 25 minute Dragonfly lesson, although I would love to talk about CT Reconstruction at length. Maybe I should do a lecture series on that. Now, what we are looking at here in Dragonfly is a data set. The idea for today's lesson is if you collect projection images with an X-ray imaging system or a neutron imaging system, or really anything that computes projections, and by projections you might mean shadowgrams, or you might mean, really it's very similar to a mathematical projection. Of course, there are different physics of interaction with the bombarded particles with the sample that may cause scattering and nonlinear effects, but effectively it is or can be thought of as a mathematical projection. Let's look at this data set. If I go through the different slices, it looks like I'm seeing the sample rotate, and that's because the sample was rotated in between a lamp and a detector, and these images were recorded. This is not the reconstructed image. These are the projections. Anytime you are working on a CT system, whether it is a laboratory micro CT system or a neutron CT imaging system or a synchrotron X-ray CT imaging, anytime you're working with one of those systems, you are recording a set of projection images that must be mathematically reconstructed into the 3D reconstruction. So today's lesson is for those of you that want to use Dragonfly to perform the CT reconstruction. Now, I will note that if you are buying a laboratory CT system, it will absolutely come with a CT reconstruction engine. They wouldn't be able to sell it successfully in the market if it didn't have a reconstruction engine. So this is for those of you that either are not using a laboratory system, or for those of you that may be using a laboratory system but you wish to experiment with the CT reconstruction parameters. Now, there is an important distinction of the geometry of illumination between systems where the photons or the bombarded particles that are incident upon the sample are either coming at the sample in parallel rays, or they are diverging from a point source and generating what we call a cone beam geometry. Those are two very different cases that have different mathematics required for the reconstruction. Today's lesson, we will show you that the new CT reconstruction engine that is launching in beta with the 2020.1 release does allow you to do both the reconstruction of parallel ray and cone beam reconstruction. Now, you must load your data, and once you have the projection data loaded in Dragonfly, then you're ready to start the workflow, and you will find it under Workflows, where you'll see the option for CT Reconstruction beta version. This is the launch point. What you're looking at is the dialog for CT Reconstruction. You'll see that you have the input image is the first parameter, then choosing a reconstruction engine, some pre-processing parameters, looking at the output dimensions, then the ability to compute previews and reconstructions. Now, what we have at the top is what is the projections data set you will be using. This is a drop-down box which will give you a list of all the available images that show up over here. I only have one image stack in my workspace. This is labeled Cone Beam Example ETS. This is an example of a projection data set collected on a Nikon micro CT imaging system, and these data are shared with us from Morgan Letourneur at ETS at École Polytechnique in Montreal. So thank you, Morgan and his advisor and his collaborators, for sharing these data with us. If you have any laboratory CT system, you may have your own projection data. Sometimes the data are not easy to access. Some vendors may encode the data in a proprietary file format, or they may bury it in a folder. But if you're lucky, or if you know where to look, then you can get those data if you wish to experiment with the reconstruction engine. If you're working with data that you get from a synchrotron, then they're very easily going to hand over the projection data, and you'll know exactly what to plug in here. Now, the first part of the workflow is choosing the Reconstruction engine. Currently, there are two Reconstruction engines offered in the Reconstruction module. The first is RTK. This comes from the Open RTK Reconstruction Toolkit available that provides a solution for cone beam reconstruction. The second option you will see is the Parallel Beam Reconstruction option, and this comes to us from Tomopai. Specifically, it is the GridRec Reconstruction engine, but also I think there is an ART Reconstruction engine. We'll look at that actually we'll look at it right now. So the data that I have loaded is cone beam. I don't have a parallel ray or a parallel beam reconstruction engine data for us to look at today, but let's suppose just for a moment this was parallel beam. I would select it. Now the reconstruction engine for parallel beam is going to show us these parameters. For algorithms, I could choose GridRec or ART. When I choose the different algorithm, I do see a number of options available here. Now I'm going to pause just for a minute and see if there's an issue since I'm getting so many Q&A. All right, just making sure these questions don't need to interrupt my presentation. So I will come back to the questions at the end. As I was saying, once you've loaded the reconstruction engine, you have different parameters. So the first is the algorithms. ART is algebraic reconstruction technique, and then GridRec is the reconstruction engine. Gosh, I wish I could give proper attribution. I want to say that GridRec is done by workers at Argonne Laboratory. I bet there's someone listening who can tell the rest of us the proper provenance of GridRec so that we can properly acknowledge them. If you do know that, would you put it in the Q&A so I can acknowledge them at the end of the talk? So those two reconstruction options are available. You'll also note that you have to identify the geometry of the projected images. That is, what is the starting angle of rotation and the last angle of rotation. And then it will assume, in this case, a linear step of projection increments. You can also define a mask. You can also set the center of rotation or ask Dragonfly to find the center of rotation. The center of rotation is a single dimensional parameter. This is the position in pixels of the y-axis. Let's suppose that the rotation of the data happens on the y-axis. The only parameter you need to know for rotation is the displacement left to right in the image. So for example, if the rotation is in the center, when I scroll through this, it will look like it's rotating in the center. So if I had it over here and this was the full frame of the image of the center, you'd see the rotation is here and not in the middle. So that's if you've done this before, then you'll understand. You're basically just determining the center. So if this was a 1024 pixel image in the x-axis, we're trying to determine the position of the y-axis, and of course that's going to be measured as an x position. So if you had 1024 pixels wide in x and it was right in the middle, then you would mark 512.0 in the x-axis as the center. And this can be a floating point number or a decimal number, so this could be 512.0 or 512.2, etc. Now, we're not going to be working with parallel ray, so we're not going to look at the iterative algebraic reconstruction technique. You can see that you can input a number of iterations here. We're not going to be working with ART or GridRec today because this is a cone beam example. Now, if I switch over to cone beam, we can move forward, and then after I do that, we will continue to look at the parameters down below. I'm going to select cone beam. And now I see my reconstruction engine is set for me. We only have the one reconstruction engine. And what you see in here are all of the parameters, again, the geometry parameters that must be specified so that the reconstruction engine knows how to position each projected image in the projection space. So the first parameter is source to detector. So this is the light source, the lamp or the illumination source, and the distance between it and the detector. This will be measured, oh gosh, it doesn't say. Here it is, be measured in microns. The second is the source to isocenter. So this is the distance between the lamp source and the center of rotation of your sample. The next steps, the next parameters are the initial angle of rotation and the angular step. The next parameter is source offset. So this is source and detector offset can be a little bit confusing. In the medical literature, it is often described as the, you can think of the sample being moved relative to the lamp and detector, because in medical systems there is a gantry with the lamp and detector at fixed positions that rotates around a sample. Most laboratory systems actually keep the lamp and the detector stationary and move the position and move the sample. There are many variations on this, though. A number of the industrial systems. There are also some laboratory micro CT systems from Tescan XRE where this is not true, where they actually move the lamp and detector. But basically here the idea is the center of rotation may be offset with the optical axis. And so that is what you were defining here, an X and Y offset in this case in microns. So if your rotation center, again, here you're determining the distance of the rotation center from the lamp. Here you're determining the offset of the rotation center from the source and the offset of the rotation center from the detector. So the source detector forms that optical axis, and then we're comparing those offsets with respect to that optical axis. The last parameter is the detector angle. This will normally be 0 degrees, but there are, of course, 2 parameters for defining the angle of a plane, so 2 angular degrees of freedom. And this is almost always going to be 0 in most laboratory systems. You can have systems, you can maybe think of laminography systems, you can have systems where the detector and the optical axis is not normal to the detector. So maybe the detector is rotated out of plane with the normal to the optical beam. So you're going to leave that, probably 99% of the time, you're going to leave that as 0 and 0. Now, the good news is you shouldn't have to encode all of this information by hand most of the time. These parameters should be documented for you in some sort of file on your system. Now, we endeavor to create readers for those different files. So as an example, we have implemented readers for the Nikon systems, the KA imaging systems, and the North Star imaging systems. We look forward to you using these and telling us if you have any issues or if there is any parameters that don't seem to be decoded properly. If I choose Nikon and now I see an option to import from file, I can click this button and now browse for a file. It's usually in the XTEC-CT file format, and when I open it, it will populate all of these fields because it has recorded the distance of the source to the detector or the source to the center of rotation, the angular increment, the offsets, etc. Now, as soon as I tried to open this, it is telling me the spacing parameters of the data set you are trying to reconstruct do not match those contained in the manufacturer file. Do you wish to apply the spacing values contained in the file before continuing? I'm going to click no so I can emphasize this point. If I come over and I look at my data, I imported this as a stack of TIFFs. And when you import a stack of TIFFs, you always need to tell it the pixel size. It may or may not decode the pixel size correctly. This stack of TIFFs says 84.66 microns per pixel. That is not correct. What should be written here is the actual pixel size on the detector. And that is part of the parameters of your CT imaging experiment. If it is encoded as 84, but this file says it is something else, it will trigger that flag. So if I choose import again, it's saying it doesn't match, so I'll click yes. Now it has rescaled the image because I clicked yes, and so now it's rescaled 200 to 200. The Z parameter doesn't matter so much. It just needs to know the pixel size of the detector. So now it's populated all of these fields and we are ready to go. Now we would like to, I'm also going to hit rescale since it's resized the image. Now I would like to add support for SkyScan and ScanSco and other instruments. So if you'd like to work with us and help identify the instruments that are high priority, then we can work with the vendors, or if necessary, just look at the files and decode them ourselves to determine what the parameters are. All right. Now, I have all of these parameters encoded, so let's move forward. The Reconstruction Parameters dialog lists an algorithm, so the only algorithm we have at our option right now is the Feldkamp or the FDK algorithm. You do see 2 parameters here, or 2 checkboxes. The first is compute on GPU. If I deselect this, then it will compute on CPU. If I enable this, then it will compute on the GPU for a GPU accelerated reconstruction. This does require a CUDA enabled GPU, so this is going to require NVIDIA GPUs, not AMD, or I guess what we call ATI GPUs now, and not Intel GPUs. Now, we could choose iterative, in which case it will allow us to set a number of iterations. If you know anything about iterative reconstruction, after each reconstruction, the reconstructed model is forward projected, and then those forward projections are compared to the experimentally observed projections in order to improve the reconstruction. So you basically are reconstructing the differences and then subtracting that from the image and iterating until you converge. There are two forward projected models, one marked Joseph, which I believe comes from the RTK, and the one marked CUDA Raycast, which is the Joseph forward projector model but implemented on GPU. So CUDA Raycast is default. We intend to provide more forward projection methods in the future. Now, if I do this, then it's going to do a number of iterations and it's going to take longer. Now, if we look forward, if we keep going down, we see there are more under advanced parameters, you'll see that there are filter parameters that can be applied. If you know anything about weighted back projection, or you know anything about CTE reconstruction, you know that your data are oversampled at lower frequency, and so if you don't do a weighting function, then you will have data that are oversampled at lower frequency, at lower resolution. So you have different filters for doing that. So you have Shep-Logan filter and hand filter and Hamming filter, so different apodization functions. You can read about those online. There's a very nice page on Math World that I looked at 20 years ago on those apodization functions that's still up to learn about the Hanning and Ham, etc. filters. Now you can choose those or you can leave them alone. Then we can look down below. There is pre-processing. So when you are doing CT reconstruction, each image must be corrected based on the detector's response function. This is called flat field correction. You may have a stack of images that has already been processed, which is the case here. If it has not already been processed, then you can do that here in this tool. You will need a single image of the same XY size that represents the bright reference or a flat field illumination. This means if the lamp is brighter in the center and darker on the edges, all the images will be corrected so that they are weighted normally and you're not over counting the photons in the middle where you may have more incident photons, but it doesn't tell you about the structure, it just tells you about the illumination. So you can specify an image there. And likewise, for the dark reference, this is what is the detector's response for example, a 100 millisecond image. What is the dark reference? So that tells you the background response. And so these two are used in the flat field correction. You could also median filter your data in the projection domain to try and remove maybe some zingers or try and correct some of the, just try and denoise the projections. Now, I'm not going to use either of that today. Now, looking down below, you can see the output dimensions. For the beta release, you are not permitted to change these. This is defined by the geometry of the image. In a future release, we will go ahead and add the ability where you can reconstruct a slab at the top of the image or the bottom of the image or some subvolume. But for now, your only option is to reconstruct the entire 3D data set. Now, looking over here, you can see that my images, the recorded projections, are 1677 pixels wide, 2000 pixels tall, and depth 2635 basically means I have 2635 projections of the sample rotated over presumably 180 degrees. I haven't looked to see if there's 180 or 360, but this is the final parameter here is the number of rotations. So 1677 is the extent in X, 2000 is the extent in Y, and then the Z parameter or the Z parameter is normalized, I guess, to the X. I have to ask my colleague what the heuristic for the Z parameter there is. Now, at any time I can hit compute preview and it will use the current parameters to compute a preview. Now, there is an issue with this beta release where it tells me I don't have enough memory every other time I think I hit compute preview. So I'm just going to have to say, please be patient, dismiss that warning, and click preview again. Now, what we have here is we have a reconstructed slice. Sorry, let's just trying to get this out of the way without covering up my captions. It's kind of hard. I'm going to position it right here. So I have a reconstructed slice. So we're not putting it in a different window, so you will see it in the same domain over here. But if I hide this for a second, we could look at it. So here is the reconstructed medial slice right through the middle, which if you're thinking about the cone beam geometry, you can think this is very much like a fan beam geometry when you do that single slice right in the middle. That is a preview. Now, if I were to come in here and I were to change the parameters, so if I went under advanced parameters and I said, let's now apply a Shep-Logan phantom, but have a much lower frequency cutoff, and I click OK and I do compute preview again, it's going to compute a new preview. And you'll see the preview up here with preview 2, and it's going to have different parameters. And so you can see a difference between these two images. Now, you could do this a number of times and then say, I wish to proceed with the reconstruction, and say preview number 13 looks the best, and say, darn, I don't remember what parameters I had dialed in. That's no problem. I could just say import inputs from preview. So if I go back to preview 1 and click OK, it's now populated all the parameters, including that image filter setting with the settings from preview 1. So all of your parameters are encoded. For that matter, when you do any reconstruction in Dragonfly, all of these parameters will be encoded in the reconstruction that you make. So you'll have access to all of that later if you wish to introspect and look at the data later. Now, we've looked at compute preview, we've looked at import inputs from preview. There are two more buttons on the interface. The first button is Reconstruct and Load. Now if I click this button, it's going to try and reconstruct the entire image stack, and it is telling me not enough memory available, and I'm pretty sure I don't actually have enough memory available to reconstruct this entire data set on my computer. This data set is if I click here, this data set, the projection data account for 16 gigabytes of data. The reconstructed image, I think, will be in float, and there may be 2 copies of it at a time. Anyway, I would run out of data. Sorry, I would run out of memory. I do have the option to reconstruct and save to disk. In that case, it will reconstruct in slabs and then write it out to the disk, so it never has to fit the entire reconstruction in memory. I should mention that because we are working on the GPU, which has limited memory, this whole reconstruction process will be slabbing the data. It'll automatically determine the slabs for you based on the amount of GPU memory. All of this is to say you cannot fit all of the projection data and all the reconstructed data on the GPU at once, and so it subdivides the problem for us. And that's really a big difference between what we're providing here and what you could get if you used these free tools such as RTK and TomoPi. One of the differences that we're providing here is we are doing the automatic slabbing. There is a little bit of slabbing in some of those tools, but it's not as advanced as what we do here, and the slabbing will allow you to obviously tackle larger problems. Okay, now if I'll hit reconstruct and save. I think it takes 17 minutes on this data set on my workstation. I'm using a $500 GPU, so I don't know if we'll have time to look at it today, but I'll initiate it just so you can see. When you do reconstruct and save, it does prompt you to input a folder, so I'll call this the lesson 36 reconstruction example. And it's not iterative, it's one iteration. Well, anyway, all the parameters will be encoded in the file, so no problem. And I'll do hit enter. Oh wait, I should be renaming it here. How do I rename the folder? Right click, rename, and call it lesson 36 recon example. All right, now it's selected, and it starts. It's telling me not enough memory. Let's do it again, reconstruct and save, hit the folder, and there it goes. It's underway. So I think it'll take 17 minutes. I don't know if we'll look at it, but you did see that you can see the individual reconstructed slices. Okay, it is 25 minutes past, and we have lots of questions, so I'm going to toggle over to the Q&A. Here we are, questions and answers, and let's pull up the questions. I've got 14 questions ready to go. All right. I'm going to start with the question at the top. Is this function going to be compatible with XRadia data format? And it looks like there are some follow-up questions. You can export XRadia projection data as TIFF images. All right, so let's see. Short answer, I guess no. Longer answer, yeah, for sure. So the XRadia data format is encoded in a proprietary format called TXRM. If you have an XRadia system and you pay for maintenance on all of your software, then you'll be up to date and you will have something I think they call Data Explorer, which allows you to transcode your images from TXRM to TIFF. And it also allows you to export a number of parameters such as an offsets table. It turns out that the way the XRadia reconstruction data, the XRadia projection data is collected, to the best of my knowledge, I don't work for XRadia and I can't speak on their behalf, but to the best of my knowledge, each image has a slightly different displacement in X and Y from every other image, so you would need to compensate for that. I believe I'm not sure, but I believe when you export using Data Explorer, it may actually export with those XY displacements corrected. You'll also need to get from that export the projection angles table. So you may read that and then maybe you can just type in the parameters. Should be able to do manually. We won't be implementing the TXRM decoder because it's proprietary to X-Radian and it's not something they've asked us to do. All right, I'm going to move on to the next question. Why not have a parameter set for Zeiss Versa systems? Well, the Zeiss Versa ships with their own reconstruction engine, so so you can use that. I guess they don't see there's a reason to have us support it in Dragonfly, but I think basically when you're buying a lot of these systems, you already have a reconstruction engine, and so those vendors are trying to take care of you. We're really providing this for people that don't have a reconstruction engine or have a specific set of experiments that can't be handled with the reconstruction engine from the vendor. All right, there's another question on deep learning methods that was asked at the beginning of the hour. I think you were asking about how to choose the depth of the neural network model. Well, the deeper the model, the more activation layers, the more complicated it can be. It usually takes more training data to converge, but it can solve problems that are more demanding. So if you've got complicated and diverse imaging input, then use a deep learning model with more layers. All right, the next question is, when can we get Dragonfly 2020 to test this function? If you are subscribed to the SEP webinar series, then you should have gotten an email last Saturday telling you about the topics for this week, including where you could go to download Dragonfly 2020.1 release candidate. So you're welcome to use that. Next question is, am I using Dragonfly 2020.1 or 4.1? I am using 2020.1, and that's mentioned at the beginning of the webinar that we're using 2020.1 release candidate 2. The next question, do you support any method for reconstructing with fewer projection images such as DART or similar? I suppose by DART you mean discrete, angular? No. Gosh. I suppose by DART, Hart. You mean Hart. That's why I can't figure out the acronym. Maybe you mean Hart, and I'm just guessing here. X-Radia offers a solution. Oh. Okay, I guessed wrong. Fewer projection images. So the ART reconstruction algorithm is implemented in the parallel ray, but not in the cone beam. So there's currently only Feldkamp for the cone beam. There are other reconstruction engines that you can use outside of Dragonfly. So you can use the reconstruction engines from TomoPi using the TomoPi interface and toolkit. You can, of course, use OpenRTK if you want to program your own solution. There's also, I'll refer everyone, the workers at University of Antwerp. I don't know them personally, but they have a very powerful toolbox called the Astra Toolbox, which you might like to use. We wanted to include that, but their licensing won't permit us to use it. It will permit you to use it for free, and it has a number of advanced options, so you may find the algebraic reconstruction technique you want there in the Astra Toolbox. Or if you really like that and you want to see it in Dragonfly, maybe you could ask them if they want to come to some sort of licensing terms or make it possible for us to use. So we're certainly interested in making those sorts of functionalities available to our users. All right. Now, next question, what file type are unreconstructed CT images typically? I'm struggling to find the data in its non-reconstructed state. Well, so Morgan from the American Museum tells us that the GE machine stores them in TIFF files. As I mentioned, the Zeiss stores them in TXRM files. The Nikon stores them in TIFF files. Every vendor has their own solution. If we have anyone from Rigaku listening, maybe they could tell us what the files are stored in. Those may be TIFF or they may be their VOX file format. So there are different file formats. I do want to mention something. I did say that we support parallel beam and cone beam, but I forgot to tell you that in addition to synchrotrons and neutrons, actually I don't know about neutrons, in addition to synchrotrons using parallel beam, there are at least 2 laboratory systems I know of that use parallel beam instead of cone beam, and that is the Rigaku Nano 3DX, which uses which uses parallel beam, and also the Zeiss X-Radia Ultra. The Zeiss X-Radia Ultra uses parallel beam. To the best of my knowledge, or at least from what I can think of right now, every other laboratory system out there uses cone beam. I'm sure there are exceptions. Okay, someone else writes here that synchrotrons store their data as H5 files. I'm sure they have lots of utilities for exporting the H5 files into TIFF. If you want us to support Diamond or ESRF, then just have their developers contact us with the documentation of their H5 file formats so that we can support that here. Next question, Morgan says, please add the GE reader. Okay, let's get in contact. And then someone else says, we would like that as well. We currently have a Nanotome M and older Micro CT Explore SP scanners. So get in contact with us and we can see what we can do to add those file formats. However, even if you don't have the file format, as long as you have the TIFF files and you know the right file to look into, it's often encoded as a text file somewhere in your system. Knowing the right file that tells you the geometries, you could just type it manually. So I'm not saying you want to do that. Obviously, we want to support the file reader, but I'm saying you wouldn't have to wait until we had a reader. You would be able to, in most cases, just type the parameters, at least to get you started in the short term. Is there any plan for implementing reconstructions for other imaging modalities, helical imaging, super sampling, or add pre-reconstruction parameters? So 2 questions there. The first on helical. Not currently looking at supporting helical. I believe all helical reconstructions that happen have to license it from eye tomography. I haven't talked with those guys in a little while. We could add it, but it would have to be a pay module, and it would have to obviously be better than other platforms, or no one would buy it from us. So we'll have to look into that. If you're doing helical, I'd like to hear more about it and why you're not satisfied with the solution you have from the vendor. Pretty sure everyone that's doing helical is using the same Kasevich algorithm for exact reconstruction of helical data. And like I say, that's licensed, I think, exclusively through eye tomography. Now, the second part of the question, other reconstruction parameters, beam hardening, noise filter, ring filtering. So we'll add that into the workflow as we move forward. But since you're already in Dragonfly, you can use any of the image filters you have that may apply. Now, beam hardening is not something, well, we should build an entire webinar on how to put this reconstruction into the context of a proper reconstruction workflow, and maybe it should be a multi-part series where we discuss what's involved in the imaging physics and what are the artifacts, so you understand what the source of them is and how you should be tackling them. So it's not already built there for you, but if you do know the physics and you want to use the existing Dragonfly filters or add Dragonfly filters, then you can filter this image just like you could filter any other image stack in Dragonfly. I will make one point. The image filtering toolbox normally operates on the XY images or the Z stack. In this case, that means your filters are going to be applied to the image or the projection domain. If you wish to have filters that work directly on the sinogram domain, then you would need to do an axis swap, so you could look at the XZ images instead of the XY images. I'll just switch over to Dragonfly. Oh, I can't because it's still working. I was going to show you the sinogram domain, but not important for now. Okay, next question. Can you find the center of rotation automatically? So you can for the parallel ray illuminations, but it's not... my friend and sometimes collaborator Dula Parkinson at ALS tells me that the algorithm for doing that works well 80% of the time and fails spectacularly 20% of the time. So you do need to inspect it if you're just doing an automatic determination of the center of rotation. All right, next question. Where can we register for the next webinars? Thank you. So what I intend to do is create an agenda and publish a seminar series for next week, and we'll register everyone for you, because otherwise a lot of you won't know about it in time or will miss Tuesday's webinar. Quick note, Monday is a holiday in the United States. We won't be having a webinar on Monday, so the webinars will resume on Tuesday. So hopefully we'll get the webinar series up and posted and get everyone who is currently registered. We'll just renew them, and maybe we can put your names in correctly this time around. Next question, how come the reconstructed pixels are not square? Meaning the X and Y pixel size are different. Well, they were the same in my example. They were different in Z, but in X and Y they were square. Next comment, the pixels will be squares or the voxels will be cubic. Those dimensions are the volume. So instead of the reconstructed volume, the shape will have a parallelepiped. In our reconstruction, I think everything will have the same voxel size. Maybe I didn't look closely at the parameters for the output data size. In the interface, the X and Y plots appeared to be different. Okay, you guys are debating with each other. We can, I do have a cancel. I'll just hit cancel, and if we wait a moment, we'll get back to the interface and see what it says. All right, next question. How much difference between the Dragonfly Reconstruction and Nikon's own reconstruction software? I expect the results are pretty much the same if I compare them. Well, I do too. So I should have led off that we're not introducing anything innovative or anything that's going to be life-shattering here. We're not claiming to have a novel or improved reconstruction algorithm. We're just making it easier to access. So if you already have a reconstruction engine, you're probably not going to have much to gain here unless you just want to take advantage of the iterative reconstruction solution. Now, I'll continue answering that question in just a minute. So voxel size, geometry size. Okay, if you look at the voxel size, it is the same. Looks like it's about 52 microns per voxel. The output geometry, the horizontal extent in X is, can't be right. It can't be 87 nanometers. I'll have to check with my colleague. This geometry here is supposed to tell you the horizontal field of view, the vertical field of view, and then the Z field of view. So these will be different depending on how many pixels you have. I don't know why. I suppose this is in some other units. Oh, you know what? This needs to be fixed. This is not 5.2 times 10 to the minus fifth microns. This is clearly 5.2 times 10 to the minus fifth meters. And so I think this is probably also in meters, which would mean this has a horizontal extent of 87.2 millimeters, 104 millimeters vertically, etc. So the pixel sizes are the same. Now back to the question, will the results be different? They could be if you use the iterative reconstruction, and we're working to build new reconstruction math that will improve this. We also have some methods underway to clean up the sinograms and clean up the projection images. We have some deep learning based methods that will improve and help correct for beam hardening and for X-ray scatter, which can make a dramatic difference. And those will all be introduced in not in the free version of the CTE Reconstruction engine, but in the premium version of the CTE Reconstruction engine. So we don't have a release date for that. It's still work that's underway. And the premium Reconstruction engine, if plans hold, we'd still be able to permit that for free use on the non-commercial license, but our commercial users would need to pay for that as an add-on. Whereas I will say our commercial users do have access to this CTE Reconstruction engine for free. So because we've not really added anything except a little bit of slabbing math and the integration into the user interface and iterative reconstruction. Apart from that, we haven't added anything over what's available free. These are just free algorithms. So we don't feel good trying to charge you money for what other people have developed and made available for free. Now, as we continue to add on this and add deep learning integrations, we will make the premium reconstruction engine a premium solution that you can pay to upgrade to. All right, the next question. When you use median in pre-processing, do you integrate or average all projections to identify detector abnormality hotspots, or do you do this for each projection? Well, the median is just done on a 2D image on every image, so it's not actually looking for those hotspots. If you have hotspots and they haven't been processed, we would need a new filter in the image filtering toolbox to find those. I think the word zingers is often used to describe what you're talking about. So I'll have to check with my colleague, and you can email me to make sure I answer this later. I'll have to check with my colleague and see if we have a zinger filter that'll take care of that. Next question. Can non-commercial Dragonfly 2020 read X-Radia TXM file now? I recall only the Dragonfly Pro can read TXM, but not the non-commercial version. That's correct. So Dragonfly Pro is the Zeiss version of Dragonfly. You don't buy it from us. You buy it directly from Zeiss. If you are using an X-Radia dataset, if you have an X-Radia scanner and you want the full Zeiss features of Dragonfly, then you would buy Dragonfly Pro. That includes the ability to import TXM files. So that's a proprietary file format owned by Zeiss X-Radia. radia, and that's only available in Dragonfly Pro. So the Dragonfly version that we make available to our customers and that we make available for non-commercial does not have the Dragonfly Pro features. So if you need the TXM, then you can look at buying Dragonfly Pro from those resellers. What is the Reconstruction format? It will output as TIFFs, or if you do Reconstruct and Load, you'll just have a new image channel here, which you can always save as whatever you want. You could save it as TIFF or save it as ORS object or RAW, etc. Next question, Ragaku uses RAW, not proprietary. Excellent. So you know that Dragonfly can import RAW files at any time. So instead of importing the TIFF files, as we did for the Nikon, you would import RAW, and then you could just tell it the bit depth and the X, Y, Z matrix dimensions, and you're good to go. And now you can use our reconstruction engine. Another vote for the GE reader. Okay, noted. Can we combine Python API with CTE Reconstruction so we can implement extra filters? Yes, you can. So I'll have to check with my colleague, but I'm pretty sure this button right here, there is an interface method, which means you can script it, but all of this is Python code that you can access, so I'm sure it's documented in the CTE Reconstruction Python module. In fact, if you open it up, if you look in the source code, I can't tell you where to look right now, but when we ship the release candidate, you can see that all the code for this is in pure Python. It's not hidden from you, so you can see all of the methods that we're calling, and you could recall them on your own. So it is available and usable for you. Next, seeing that this is our last daily meeting for the series, what is planned for the future? Well, this won't be the last. We will do 4 more lectures next week, or at least that's my plan. I hope I'm able to come through on that, but the current plan is 4 more lectures Tuesday through Friday. Now, what I hope to do is come up with a recurring webinar series with lower frequency, so not every day, probably not even every week, but something to keep us engaged and keep showing you what's new, but also show you applications. A lot of what we've done over the last 36 lectures is show you the tools in Dragonfly that you have. What I would like to do is start a series that shows you how to recombine those tools in useful applications. So for example, how do I analyze my industrial parts using the existing tools? Maybe I'm looking for porosity or actual nominal comparison. How can I do that in Dragonfly? Maybe a lesson on I'm examining powder grains and I want to characterize them and write reports on powder grains. Certainly an application on bone studies. What's the best way to get everything I need in bone using the tools in Dragonfly? Or maybe one on identifying and tracking nuclei in confocal images. I don't know that we can actually track them, but that's an example of the sort of application we'd like to see and demonstrate when you put together all the tools. So I think what we'll do is probably build an applications series, and then probably next year, if I can get funding and approval, I'll put together an image processing series where we can dive deeply into what are the image filters doing, what are the alignment scoring functions doing, how does deep learning math work, something that would give you not just the practical application, although it would focus on practical applications, but help you understand all of the parameters of the image filters and, what do we mean when we talk about high frequency and low frequency in image domain? What is a Fourier transform? Why is it that CT reconstructions oversample the low resolution space? So I would like to, as I say, get approval to do a lecture series on image processing, which I think would be interesting. There's a lot of good lectures on the internet for that on YouTube, but I think integrating them all together specifically for scientific imaging with a focus on X-ray CT, but also EM, I think would be a useful lecture series. So in the short term, let's see if we can get next week's lectures and get the Dragonfly Daily wrapped up for May 2020. Then in the medium term, let's build an application series of topics. And then in the long term, let's build an image processing lecture. So anyone that's new to scientific imaging can start at the beginning and understand what are all the consequences of these different imaging modalities. That's something else that would go into the lecture series, or what are the imaging physics of the interaction of X-ray photons with my sample, or when I'm bombarding a sample in the electron microscope with 1 keV electrons, what's happening, and what is the backscatter detector detecting, and what is an EDS detector measuring? Those sorts of things would be quite useful. I see another question. Oh, no, it was just an upvote on having an image processing lecture series. All right, you guys had a lot of questions on the reconstruction engine. Honestly, I'm not quite sure why everyone is so interested in having a reconstruction engine, since almost everyone already has one. But you guys are interested, so now you have one you can start to play with and give us feedback. We will continue to update it. The Dragonfly 2020 will ship soon, but we'll also have 2020.2 coming out this summer because there are some things we just couldn't fit in for 2020.1. So when 2020.2 comes out, we'll have some more enhancements and a few more things will be worked out with the Reconstruction engine. Maybe if some of you work with us to get this GE file reader, maybe we can have that built for you too. No promises, but seems like a reasonable goal. So thank you all for your attention, and thank you all for joining me today, and I look forward, hopefully we'll have another lecture on Tuesday. All right, everyone, have a great weekend, stay healthy, and see you on Tuesday. Bye-bye.